Now let's observe the behavior of light in different circumstances like this. So let's say we have a glass slab, okay, and it has a refractive index n1, and we know that it is always going to be or greater than 1, right? So 1 for the vacuum, so it is not vacuum, so it is going to be greater than 1. Now, so which means that if this is air or vacuum, this is a denser medium, okay? So this is a lighter medium. The glass is a denser medium. Okay, so now we have a light ray which we are going to bring in. It's going to hit here. So what we are going to do first, as we said, first we try and draw the normal. So we perpendicular line, right, like this, meets at the origin. This is our normal. Hence, this angle here is going to be the angle of incidence. Okay. Now, can we simply predict this how this light ray is going to go? So if there was no refraction, basically it will go straight like this in the same direction. But there is going to be a refraction, so it will not move in this direction, but it is a denser medium. So can you guess that if the light will bend here or towards the normal like this? As we said, the light is traveling from a lighter medium to a denser medium, so it is going to bend towards the normal, and this is going to be our angle of refraction beta, and we can simply find that beta using Snell's law by writing n1 sine I is going to be n2 sine beta, right? Sine of beta is going to be n1 sine I divided by n2, and then we can find sine of beta. Now once the ray of light comes here, what happens to this ray of light? So basically it is going to proceed from here all the way, I'm going to come here. Now as again there is a change of medium, right? So this ray of light is going to again experience refraction. So how do we solve this? Very simple. First step, we are going to draw a normal. So where is the normal? Perpendicular to this is our normal. So here again this angle here is going to be our angle of incidence I2 in this case here, and this is going to be equal to beta because this is drawn from the normal and this is, these two perpendiculars are parallel to each other, right? So I2 will be equal to beta, and now as it tries to cross this to the different medium, now it is going from a denser medium to a lighter medium, right? So now if there was no change, if there was no refraction, we expect this light to go like this, right? But we know it is going to be, it is not going to be go very straight, but it is going to be refracted. Now it is going from a denser medium to a lighter medium. So can we guess the light ray is going to travel like this or away from the normal like this? As the light is going from a denser medium to a lighter medium, we expect the light ray to refract away from the normal, and hence it is going to be like this, not this. Okay. So let's delete this one. Now you will also observe that this is parallel to this one because of law of reversibility. So if we are going to put the light ray from here, it is going to trace back the path and going like this. So this angle is again going to be equal to alpha. Sorry. So this angle is going to be equal to I, same as the angle of incidence, right? But this ray will shift little bit from the path. This is going to be parallel to each other, but there will be a net shift d of the light ray. So we can simply understand the behavior of light rays in different scenarios using Snell's law. So let's go try and understand a different case such as a prism. So prism is nothing but, let's say something like this here. So this is a prism. As we said, we are in air. So here it's made of glass with a refractive index n, so it is a denser than air. Right? Now we are going to put a light ray like this. So what will be our first step? The first step will be to find the normal. Need to be able to draw the normal perpendicular to the surface like this, which means that angle over here with the normal is going to be our angle of incidence I. Now, if there was no refraction, we expect light ray to proceed straight like this, but we know there is going to be a refraction because there is a change of medium, so the light ray is going to bend, right? Now, will it bend away from the normal or towards the normal? We know that light is coming from a lesser denser medium to a denser medium glass, hence it is going to bend towards the normal, which means it is going to be from here, it's going to bend like this towards the normal, right? And this angle here, the small angle here, will be of course smaller than alpha, and this is going to be beta, which will be our angle of refraction, and we can compute that using Snell's law. N1 sine I is going to be N2 sine beta. We know that N1 is in the air, so this is 1. So 1 into sine I is going to be N2 sine beta, and we can simply compute beta from this equation. That's very simple. So as you can see, it doesn't matter whether it is a prism or a block of glass, the Snell's law is always going to work, right? So to extend this concept, let's look at what will happen to this light ray when it goes from here to here like this, and eventually it's going to hit again the glass somewhere around here. Again, it's very simple. We are going to draw our normal first. So draw the normal perpendicular to the surface here, and this one, this angle in here is going to be our new alpha, or let's say angle of incidence. Now this alpha is not going to be equal to beta because these two normals are not parallel to each other, right? But we can always find a relationship. And now let's try and see how the light will proceed from here. So if there was no refraction at this surface, the light will proceed in a straight line. But we know there is going to be a refraction, right? So now we want to know how the light will go from here to here. So now this is coming from a denser medium to a lighter medium, which is air, right? So this is a denser medium. After this line, there's a lighter medium. So the ray will proceed in a direction which is away from the normal. So the light ray is again going to bend. So this is not the right point. So here, this on went away from normal, and this angle now, so theta will be our angle of refraction here, right? And at this point, we are going to write the Snell's law. So this medium has a density and this one has refractive index 1. So first here, and sine alpha is going to be equal to 1 into sine theta, and theta is going to be greater than alpha. Applied Snell's law at 2 points, at the point number 1 here and point number 2 at the interface where the light was changing from one medium to the another, and it does not matter whether it's a prism or a block of a glass or any other medium, the Snell's law is always valid. Hence it is a very kind of a fundamental law, and now we are going to see the same what happens when we have a surface. Okay. Start like this, and this end to this end it has a spherical shape, right? And we want to know what's going to happen to the light ray, which is going to come in this direction. Step 1, we are going to find our normal. So we are going to draw, first a tangent here is a sphere and a perpendicular to that. Hopefully this is our normal. So the angle of incidence is going to be this angle here, I, and if there is no deviation from the path, the light ray, we know that is going to proceed in a straight line like this. We know there is going to be deviation from the path, and then we can predict how the light ray will go from here to here. So this is air, this is a denser medium with refractive index n, so n is greater than 1, of course. So the light ray is going to bend towards the normal, right? So this is the normal. Let's zoom it out. This is the normal, and this is a light ray, unreflected, but in reality now the reflection will happen. This light ray is going to be get refracted and actually go like this towards the normal. Now again, when it meets the surface here, there will be another refraction, and we can again write Snell's law for this point. So first we are going to apply Snell's law at this point, point number 1. This is where the light ray is meeting. Then we are going to apply the Snell's law at point number 2. So whenever there's a change of medium, we can apply Snell's law. We can always apply the Snell's law at the point of incidence at the interface, and it will be valid. So we are able to predict that quite easily. So now let's say we have 2 slabs of glass. So one is here, we have another one, which is here, and so we are going to say we are putting the slabs in here. So this is air. This slab has a refractive index n1, slab reflecting just N2. Now we are going to direct a ray of light from the top. Let's say, and we want to know how it's going to behave. So first thing first, we want to know where my normal is. So we draw our normal, which is going to be perpendicular to this. Very well, this is our normal. And we know that if there was no reflection, the ray of light will go like this. But now it is going from a lighter medium to a denser medium. So the ray of light is now going to bend. So sorry, let's take that and will not go like this, but bend towards the normal and will come up to here, right? Now we have to predict what is going to happen over here. Again, we need to know our normal. So we are going to draw a normal perpendicular to here. And this angle will be our angle of incidence. Now we have to predict how the ray of light will go from here to here. For that, we need to know the relationship between N1 and N2. So let's assume that N2 is greater than N1, which means the ray of light is now coming from a lighter medium to a denser medium. So what is going to happen to it? So without refraction it will go straight, and with reflection it is going to further bend towards the normal and it reaches here. So within a homogeneous medium it is going to travel in a straight line, but as the medium change happens, we need law of refraction to figure out the path of light. So as it meets here, we need to again draw a normal. Sorry, let's do that. And now it is N2 and it is going to go out in air. So without refraction, we expect the ray of light go straight like this. But now, as it is going from denser medium to a lighter medium, it is going to shift away from the normal, so and such that this one is going to be parallel to this one. This angle here will be equal to this, and we can prove that by applying Snell's law at different points where the ray of light is changing or meeting different mediums. So point number 1, point number 2, point number 3, we apply the Snell's law to exactly know the path of the light. To make things a little bit complicated, let's try this one. So let's say we have n different slabs. Slab 1, 2, six, like that, and their refractive indices are variable, so they are thus like changing randomly. So this one is 1.2, 1.4, and 3, 1.6, and 4, let's say 1.5, and 5, 1.4, and N6 is 1.6 again. So now we are going to track the ray of light. So here is our ray of light. Let's draw it with a different color. So this is a ray of light. So it is going to enter this medium which is denser, hence it will not go straight, right? It will not go straight, but bend towards the normal. Yeah, so it will bend like this. Now it comes here, and now it is going to enter from 1.2 to 1.4, right? So it is going to enter a denser medium, so it is further going to bend towards the normal. So it will move, it will not go straight, bend further towards the normal like this. Now it is going to move from 1.4 to 1.6, which is again a denser medium. So the ray of light It's not going to go straight but bend further towards the normal like this. Now it is interesting. Now it is going to move from 1.6 to 1.5, which is a lighter medium. So we can say that the ray of light will not go straight but bends away from the normal, taking a path like this all the way to here. Now here it is going to move from 1.5 to 1.4, which means from a denser medium to a lighter medium. So again, it will not go straight but bend away like this from the normal, and it's going to hit here. So it is now from 1.4 to 1.6, which is a denser medium. So ray will not go like this but bend towards the normal and will go like this. Now it is going to hit this interface from 1.6 to 1. So it will not go straight, come like this, and eventually parallel to this ray, and these two angles normal to this, normal to this, these two angles will be equal. That we can prove. So we can track the path of ray of light by just applying Snell's law all the way along which the light is traveling, and that's very easy. So we applied the Snell's law here, 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 and here. We'll do the exact maths of this, but this is the basic concept that you can apply Snell's law to a different point whenever there is a shift in the position of the light moving from one interface to the other, and it will be valid. So with that, we are going to end the today's video, and from the next video we'll start solving some problems and dive deep into problem solving skills required to use Snell's law.